In this video, I'm going to talk about simple circuits, and I'm going to use the analogy with the water to explain all the parts of a simple circuit. But before we start, in order for water to flow, you have to have a difference in pressure. If there is no difference in pressure, the water will not flow. In order for heat to flow, you have to have a difference in temperature. So if you mix hot water and cold water, there are two different temperatures, so you will reach an equilibrium. Same thing here. In order for current to flow, you have to have what we call a difference in potential, or potential difference, which means we need some voltage. We need some push. So I'm going to think of the voltage as a push, as a force. Okay? So a simple circuit requires, this is the bare minimum you need. You need a battery, and that's a symbol for a battery. Now what does the battery do? It will give you that voltage. Okay? The voltage does not travel in the circuit, but it just provides the energy required for things to work. So sometimes we'll label this as the delta V or V, or sometimes we'll write it like this fancy E, which is the electromotive force for E. Okay? Sometimes this battery will have an internal resistance, sometimes it won't, but for now we're just going to do it as if the battery is ideal, meaning like no internal resistance. We also need something that will use this energy. So an example would be a light bulb. That's the symbol for a light bulb, right? Sometimes we'll just draw the light bulb or any load, anything that will use that energy as this squiggly thing, right? So this is what we call the resistance. So you have a battery or a bunch of batteries hooked up in series or in parallel. We'll talk about that in a lab. And what this battery does, it takes chemical energy, there's chemical reactions happening inside the battery, and turns them into electrical energy. And then you can close the circuit. Now, sometimes maybe you want to put a switch so you can control the flow. So that's the symbol for a switch, but it's not necessary. The switch, when it's in this position, it means that it's open, meaning like there is no current flowing. Okay? And when it's closed, then you're allowing the current to flow. So a requirement is like the circuit has to be closed for current to flow. Now here's my analogy. I think of this voltage or this battery, okay, as a pump. I'm going to do the analogy with the water now, right? So this is my symbol for a pump. And in order for water to flow, the pump will provide that difference in pressure. Okay? So, and for wires, I'm going to think of those as pipes when it comes to water. So I have a pipe here, okay? And I'm going to put my equivalent of the light bulb on this side. So I'm trying to turn a water mill. So it looks kind of like this. So as the water is falling on it, it makes it turn, and then we can use that energy to do something else. So the water makes it turn, the water falls down in a container like this, right? And what does the pump do? The pump provides that the difference in pressure so that cycle continues. So looks like this. Okay, that's a simple circuit. Now, if I want to add a switch, the equivalent of a switch will be a valve, basically, right? So I can come in here and put a valve. Okay. And then when I close the valve, there is no water flow. When I open the valve, then the water starts to flow, just like a hose, basically. Okay. So this is the equivalent. So for me, current is the flow of water, equivalent to it. The pump is equivalent to the voltage source, meaning like a battery. The valve is equivalent to the switch, and the light bulb is what's giving me electricity. So I'm doing something useful with that electricity. So here I'm doing something useful with that water, making this mill turn. The voltage does not flow through the circuit. Only the current flows through the circuit. Now, with the current, we're always going to look at it as going from the positive to the negative. That's conventional current. Because in the old days, they used to believe that it's positive charge that moved. So they say, well, conventional current has to go from plus to minus. but the way the charge moves, which is basically the electrons, is from negative to positive. So this is your negative side of the battery, and this is your positive side. So we're not going to look at it in terms of the flow of charge, but we're going to look at it as the conventional current. All right, let me see what else I have here. All right. The next thing I want to talk about is on page 9, and it's Ohm's law. And I'm going to do that quick because it's all math. So Ohm's law says, well, the voltage is equal to I times R, which really means I equals to the voltage divided by R. Now let's look at these terms. I stands for current, voltage stands for, V stands for voltage, and R stands for how much resistance, okay, you're encountering in this circuit. Okay, so this is kind of like a handicap to the flow. So if the resistance is high, you're going to have a little flow. If the resistance is low, you're going to have a good flow. Now the equivalent to this is what I like to call kind of like the equivalent of Newton's second law, because it looks very similar. Newton's second law looks like this. A, acceleration is force over mass. Okay, very similar. Now, current has to do with the flow. Well, acceleration has to do with how fast you're changing your speed. V is that energy or that push that you're getting from a battery. Well, F is the force. So this is kind of like similar. And the more mass you have, the more inertia you have, which means the more resistance to accelerate. Okay? In here, R will, if R is high, it means like your current would be low. All right? And that's it for this video. See you later.